Hello, everyone. I'm Alberto Fierro, the Consul General of Mexico in Boston, and I'm very glad to have you here for a very special conversation with our guest, Dr. Grant Wilson, on bilateral Mexico-US collaboration in terms of space and its mysteries. Dr. Grant Wilson is a professor and graduate program director in the Department of Astronomy at the University of Massachusetts. He did his graduate work in physics at Brown University, where he studied cosmology by building balloon-borne instruments to measure the cosmic microwave. Background: the oldest radiation in the universe. After receiving his PhD in 1997, he did postdoctoral work at the NASA Goddard Space Flight Center and then at the University of Chicago, where he worked on specialized experiments in the field of observational cosmology. Professor Wilson transitioned from early universe cosmology to studying the astrophysics of galaxy and star formation when he came to UMass in 2001. He has since won the College Outstanding Teacher Award, discovered many hundreds of new galaxies with the Aztec camera that he will tell us more about it, chairs the Science Advisory Board of the Large Millimeter Telescope, and now leads a multinational collaboration of scientists in the building and deployment of the Toltec camera that he will tell us more about. So as you can see, everyone that is hearing us and watching us, it's impressive, your academic trajectory, Professor Wilson, and I can imagine how fun all this conversation is going to be. But just to put in context before we start asking Professor Wilson, the telescope that you see behind him is an ambitious idea. It's called the Large Millimeter Telescope, that started in 1988 by Dr. Alfonso Serrano, that he was then Director of Astronomy at Mexico's National University, UNAM. But it was several years later, 4 years later, in '92, when he became the General Director of the National Institute of Astrophysics, Optics, and Electronics in Mexico. And he started lobbying his idea of having this big millimeter telescope in Mexico. And it was 2 years later in '94 when he finally managed to start the project with the collaboration since the very beginning, and I think this is very important, of UMass Amherst, the National Council of Science and Technology. This large millimeter telescope, Alfonso Serrano, who has his name, was a $200 million project built in one of the highest peaks of the country, Sierra Negra, over 15,000 foot inactive volcano. The location of this telescope had to be strategically chosen due to its complexity. The atmosphere had to have a low humidity. The challenges to build this at the fourth highest peaks of the country included the transportation of materials, the lack of roads, and the lack of oxygen. The construction took several years and was finally inaugurated in the year 2006, as I had mentioned. Today, this telescope is one of the most important tools for the exploration of processes that lead to the evolution of planetary systems. And now there are a lot more organizations involved that we will hear more about. But Dr. Wilson, tell us, how did UMass Amherst get involved in the large LMT project?
Well, first of all, let me say thank you for the invitation and to be here today. It's a great honor to be able to be on your program. So UMass has actually a long history in radio astronomy. So we normally think of telescopes as optical telescopes, but radio telescopes are now used widely around the world, as we'll talk about over the course of this conversation. UMass actually got involved with radio astronomy, which was a relatively new field in the 1960s. And between the 60s and the time when the idea for the LMT began in the 90s, there was a successive steps of telescopes and technologies developed at UMass and actually placed out here in Western Massachusetts, where people did pioneering studies, including some of the work that led ultimately to a Nobel Prize by Russell Hulse and Joe Taylor in the study of rotating neutron stars. The UMass, at some point in the 90s, this was before I joined the department, decided that their 14-meter telescope was too small and that they would like to build a 15-meter telescope, like the LMT now is behind me. That would make it the largest millimeter telescope in the world at the time. And they thought they would build it right here in Western Massachusetts, where we do not have low humidity and where we are not a high altitude location, and there's no mountains around here suitable. Fortunately, that group met up with Dr. Serrano and formed a collaboration, as often happens in big projects in astronomy. And when they realized they could combine both resources and take advantage of the very high altitude, beautiful sites in Mexico, they got together and started this project. And it was a very long project to get constructed. As you can see behind me, the telescope is well above the cloud levels. This is 15,000 feet, where you have about 2/3 of the oxygen that you have at sea level. So it's a very, very difficult place to work. There were no roads. So a big construction effort to get this put together. And, but over the years, we managed to do it. And as you said, the telescope was, had its first light and was inaugurated in 2006 with actually a visit by President Fox at the time.
Thank you so much, Grant. With us is Paulina Ramirez, who is in charge of the area of innovation here at the consulate. And so she helped me prepare the questions for you. So she will be asking some of the questions today during this conversation. Paulina, do you want to go ahead?
Yes, thank you so much, Consul. Well, I would like to ask you now that you have been involved for so many time in the large millimeter telescope project, we've heard that you lead the Toltec project. So can you tell us about this? What does this involve?
Sure. So when we completed the construction of the LMT, we had a camera. This is a camera that actually makes images of the sky. So that's one kind of camera we have for the telescope. We have another set of instruments called spectrometers that look at the spectrum of the radiation coming from the sky. But I had led the development of a camera called Aztec, which at the time we created it was one of the largest millimeter cameras in the world. It had, are you ready for this? 144 detectors, which at the time seemed like an enormous number. Of course, technologies advance, and we've been working, we meaning many people around the world have been working on detector technologies at millimeter wavelengths since then. And we realized about 5 or 6 years ago that we could make a much larger camera now with the advances that we've made in detector technology. And that led to the idea of Toltec. Toltec has 7,000 detectors. So wow. That's the step we're taking. It's really enormous. Mm-hmm. And we wrote a proposal to the National Science Foundation, who was gracious enough to fund the construction of the camera and its initial operation. And that's where we are now. So the advantage that brings to us, once we get the camera to the telescope later this year, is we should be able to make pictures of the sky something around 100 times faster than we could with the Aztec camera. And for a telescope, the currency of a telescope is time. because you only have so much time to use the telescope each night. And so the faster you can go with making images, the more science you are able to do. And when we offer the telescope to other people to use, so we have what we call a call for proposals. Scientists from all over the world will send proposals to our group, a joint group between UMass and Mexico, who reviews the proposals and then chooses the very best ones. And we allocate those proposals by time. So a group might ask for 10 hours or 20 hours or 50 hours of telescope time. And so what Toltec will allow us to do is projects that would have taken 50 hours will now take, just an hour or maybe less. And so now we can do many, many more projects of that size or much bigger projects.
Wow, it's incredible because it is an impressive advancement. It's like 100 times faster, as you said.
You don't get advances in your life like that very often. I will tell you that when we realized we could do this, I was talking to my friends here in the department, and some of them do very different kinds of studies than I do. And so I remember one fellow, I said, here we're going to build this thing. It's going to be about 100 times faster than Aztec. Please help us come up with projects to justify why we would build this thing. And my friend went away. He came back the next day. He said, this is really great. Oh, I've come up with this great project. And he told me about the project, and I did a small calculation. I said, well, that's really nice. So we can do that project. What would you like to do the next night? Because that's going to take us one night to finish everything you've described that you want to do. And people had to go and think of at a much bigger scale than they ever had before. So it's exciting.
Wow. And so, well, it's exciting and it's impressive, and it's a huge challenge, I understand. Tell us a little bit of which institutions are involved. You just mentioned US and Mexico. I think also University of Maryland has had something to do sometime with it. And what is the biggest challenge and how has the negotiations advanced for having Toltec being installed over there?
Right. So, okay. So in terms of the challenge, I tell my students now that, everything easy has been done. A long time ago, when I was a graduate student, the size of these projects was still small enough that everything could fit on the bench of a single lab in a single university. And, we struggled for space around what we worked on to work on it. Toltec is much bigger than this. And in fact, it requires seven different institutions from 3 different countries working on the project. We have a group at Inaue in Mexico that works on it. UMass, the Arizona State University built all of the electronics for the camera. A group at Cardiff University in Wales has made all the filters that are very specialized filters for millimeter wavelength radiation. A group at the National Institute of Standards and Technology here in the US is building the detectors for the camera. And a group at Northwestern University is making one of the key optical components to allow us to measure the polarization of the light coming through the telescope. And then finally, the University of Michigan was responsible for making very specialized lenses for the camera. So you get the idea that no single group is technically capable of building the entirety of these kinds of systems anymore. They're just every part is much too complicated. And so it takes a large, in our case, tri-national effort to be able to put something like this together.
Wow. And you as leader of this project, and your expertise is measuring and discovering new galaxies that you'll tell us more about it. But it has also made you, I guess, kind of like a special advisor as an industrial engineer or a creator of this, that you might have not imagined that you would be dealing with all the technology of constructing a telescope.
Yeah, that's right. So over my career, because I came out of a physics background and had quite a bit of engineering in my background as well, I've been fortunate to be involved in big projects. And I think one of my skills that I bring to the table is just the ability to organize and work across very, very different technological areas. So in our camera, for example, we do an enormous amount of mechanical engineering, a lot of cryogenics. That's one of my specialties, where our detectors have to be cooled to just 0.1 degrees above absolute zero. And so a lot of what we do is focused around getting the detectors that cold and getting them to be stable at those temperatures. But then we add in optics, very advanced electronics, and then very specialized software, which our group all writes together. You can't go to Microsoft or Google to buy the software that you need to produce images from these cameras. So you sit down and you figure it out and you write it all yourself. So you can see there's many, many different areas. We're really fortunate on our team to have real experts across that. And in fact, we should fight to keep industry from taking away our experts, because they pay better than science does. But everyone on the team is very dedicated to the kinds of things we want to do. And they are the world's best in each of those areas.
The project sounds fabulous, but I wanted to go a little back to the Toltec camera. And for us that have never had an experience taking images in a telescope, can you tell us about how long does it take to obtain an image from the sky?
Yeah, that's a really good question. One we actually don't know the answer to yet, because we've never used a camera this fast before to do millimeter imaging. But I can give you what we think will happen with Toltec based on what happened with Aztec. A typical night at the telescope, you get the telescope going, you choose what project you're going to focus on for that time, and the telescope will go and point at a very particular location in the sky, and you just run what we call an observational program. We actually move the telescope constantly. Because the Earth is rotating, we have to track the object as it moves through the sky. That involves the robotics of the telescope to keep us pointed in the right places. But at the end of all of that, you don't get your image that night. So at that point, you have to move all of your data. In the case of Toltec, we'll move all of our data to a cluster of computers that is capable of running the software to actually make the images. And then it will take another few days for the cluster to process all of the data we take in a big project and produce the final images. So things, as astronomers, we learn we have to be very patient. And so we will take our data for some of the big projects we're doing, where the data results will become public. We'll actually make the maps public so that any astronomer around the world can use them. But that data will take 6 to 8 months to process, and to make sure that we're getting it completely right before we release it to the public, because we don't want to put anything out that that might not be correct. And so there's a lot of vetting of the data that goes on. But it's a very slow process.
Like really slow process.
And tell us a little bit about how it has, of all the institutions that you mentioned that are involved, it's incredible how many. The only ones that speak another language are the Mexicans.
Yeah.
How has it been? I mean, I know that among scientists, almost everyone in the world has some command of English, but culturally, we do have differences not only in language, but on how we approach to doing science. How has the experience been for you working with the Mexican institutions, and how much have your students and other faculty been related with Mexican faculty and students, and has it been an interesting cultural exposure for you guys?
Oh, it's been a fantastic cultural exposure. So, so astronomy, as I was saying, of our projects are now far too big to be single institution, and now even many of them are multinational projects. And I've been fortunate to work with Japanese groups, Korean groups, and of course, our very good friends in Mexico. So I first met many of these, the people I still work with now, 20 years ago, and we have become wonderful friends. I will not lie, it's hard initially to work with other cultures. There's a lot to learn, and you have to learn about, if you don't take the time to learn about the culture, you'll just constantly be frustrated. And I think that's true for my Mexican colleagues when it comes to working with us, and it's certainly true for us with working with them. There's different structures, different times people will speak out, different times or different ways the information flows, all sorts of things like that. But I consider myself now a pretty good expert in working with my Mexican colleagues. I have a good sense of the culture. I've spent a lot of time in Mexico, in Puebla, near where our sister institute is, as well as working at the site with a lot of local people who live right in the area. And I will say it's a big learning curve, but it's been a wonderful experience overall. And I think for them as well, we've done a lot of student transfers between our institutions where students will go and work in the other place. And along with that has come a lot of technology transfer between our groups. And I think all these experiences have been just great. I'll say that, more than ever, it's important that our students here at UMass get exposed and work with both Mexican groups and groups from other countries, because as I said, that as we go forward, all of these projects are just going to get bigger, and more countries will be involved. And so they must learn to work with other cultures and study other cultures in order to be successful. I just don't see any other way.
One quick question before Paulina asks another one. I was reading the name of the Toltec. Why, if the first LMT was Aztec, which is many centuries more modern, why did you go for the most modern telescope for an older name? Was it the giants of the Toltecs?
Well,
who chose the name?
I chose the name. When we did Aztec, we actually we found a nice acronym for Aztec that we used, and that was great. And what we did with Aztec was we wanted to say, yes, we're coming to another country, and we want to give a nod to the culture of that country, or at least a part of the culture of that country. When it came time to do Toltec, we thought, well, we should have started with Toltec and then gone to the Aztecs. But in fact, we learned that the Toltecs were responsible for a lot of the inspiration, the scientific inspiration for the Aztecs. And we thought, okay, well, we'll go backwards, but it'll be yet a new nod to the culture of Mexico. And so it's just, I think what's great about it is it's such an easy name for everyone to remember.
Yeah, great. Paulina?
So I want to talk a little bit more about this international collaboration you were talking about previously. In 2019, actually, there was a really interesting project, which is the Event Horizon Telescope that took the first picture of a black hole, which is like a great advance for astronomy. So can you tell us a little bit about this project, what its relevance for the scientific community?
Yeah, well, first let me say that the large millimeter telescope was a key part of that measurement, and it was one of the many telescopes across the world that took part in the EHT project, EHT for Event Horizon Telescope. I think that the measurement I mean, I will be surprised if it's not at least considered for a Nobel Prize at some point, because this is just a critically important measurement for astronomy, in the sense that before 2019 or before the EHT results, we had a lot of evidence for black holes, but no direct detection and no direct imaging of the event horizon. And so there was always room for the idea that the black hole wasn't actually there, that wasn't a black hole, at least in a scientific sense. The EHT measurements, at least for me, really are the first step of what will be a long process of measurements with many telescopes turning the entire Earth into a telescope by the EHT consortium. And so I think what we now have is direct evidence of the event horizon. What we will have as time goes on is actual images of the material swirling into the black hole, which will just be astounding. And the idea is they should be able to make eventually movies of what's going on at the event horizon of several different black holes. Now, this is all to be seen, and there's a lot of work to do. There's a new version of the EHT project that is funded by the National Science Foundation and is underway. And so we expect the LMT will remain a part of that and continue to play a critical role, both because of its overall size and because of its geographical location, which really makes it central to the project.
And do you think that Toltec will be ready and installed by the time this next Event Horizon Telescope happens?
So Toltec isn't the receiver we use on the LMT for the Event Horizon Telescope. There's a different receiver there. It's actually a much simpler receiver. The beautiful thing about the Event Horizon Telescope is they take relatively simple receivers, but they put them all over the Earth so that you can reconstruct what a telescope the size of the Earth would have seen.
Wow.
It's a technique called interferometry.
Wow. We've learned that you have a particular interest in observing the circumgalactic zone. What is it, and what can you tell us about it?
Yeah, it's a strange name. So the circumgalactic zone, or the CMZ, is the region of our galaxy, which is at the center of our galaxy, both the geographical center or galactic center of the galaxy and where the center of mass of our galaxy is as well. So it's really the central location. Right at the center of the CMZ is the Milky Way's own massive black hole, about 4 million times the mass of our sun. So big black hole. But that doesn't dominate the CMZ. The CMZ is quite big in comparison. And there's something really spectacular about it. And that's that there's an enormous amount of gas and dust that has funneled its way to the center of our galaxy. And yet, very few stars are forming at the center of our galaxy compared to the amount of material that is there, the amount of fuel for star formation that exists there. And so it remains as a mystery to astronomy as to why the center of our galaxy isn't just absolutely exploding with the birth of new stars. Something is stopping those stars from forming. And we have made images with Aztec from the LMT of the CMZ, and we've just last year put out a pair of papers about this. We've made steps towards understanding this, but we still don't have all of the information. With Toltec, we'll be able to go back and do very detailed studies. And in addition, Toltec has the ability to measure the effects of magnetic fields and what role they can play in suppressing the formation of new stars. And we don't have a good sense of that now in astronomy, but Toltec will be a new view into that process, and hopefully will help us explain why the center of our galaxy isn't producing enormous numbers of new stars. And the Milky Way is just one galaxy. It happens to be the one we live in, but we look at very distant galaxies in the early universe that look very, very similar to our CMZ. And so our CMZ is an analog for those early galaxies. And yet those galaxies are all forming stars at maybe 500 to 1,000 new stars every year. Our Milky Way on average produces 2 or 3 new stars every year. So very low level in comparison. We'd like to understand why, all the reasons why.
It's interesting to know, sorry, Consul, yeah. But it's interesting to know that tool like this is such an elemental piece for this study, and it would be really important to have it as soon as possible installed to go on with the study. Yeah, I had one question, but I completely forgot it. So sorry, Consul, can you go ahead?
No, I was, or it makes me think how incredible it is that we are human beings are tiny compared to the planet Earth. The planet Earth is tiny compared to the sun system, and we're tiny compared to the galaxy, and you're already looking at and trying to understand what other galaxies are, which maybe some have already disappeared and we're just looking at them later, but it's fantastic. So can you tell us about your research on the history of galaxy formation and evolution? A little bit more about it.
So I'll say a few words about that. So because light travels, we think of light traveling very fast, light speed, but it's actually very, very slow compared to the size of the universe. And so we know that as we look further and further away from us in the universe, the light that we're getting now from those distant locations was emitted a long time ago. So telescopes are time machines, and we can look back about 14 billion years, or almost 14 billion years with the LMT, and see all the way across the universe. And there's a special coincidence that happens in physics that makes at millimeter wavelengths, and this is really one of the biggest important pieces of a millimeter telescope, the light that was emitted all the way across the universe is almost the same brightness when it gets to us now, but only at millimeter wavelengths does that work. And it would take me a chalkboard and some math to show you why that's true, but it's really a spectacular thing that we can look in the sky with Toltec or with Aztec before, and we can look all the way across the universe and see galaxies as they existed almost 14 billion years ago. And so over my career, since I've been at UMass, I've been doing exactly that, taking images with Aztec before and picking out galaxies over the history of the universe. Now with Aztec, we could only see the very brightest, the most massive, actively star-forming galaxies in the universe. But with Toltec, we'll do exactly the same thing, look out into space, see every galaxy along the way, and only we'll be able to see relatively normal types of galaxies like the Milky Way, all the way back until galaxies don't exist anymore. And by doing that, we first take the images, find them, and then we have to go back with other instruments, other telescopes even, across the entire electromagnetic spectrum, and then study them one by one and try to understand how the evolution goes as the universe ages and as the galaxies age as well.
Wow.
This is really interesting. Is there any other thing similar around the world to Toltec?
So I should say, let me count. There are 3 other cameras based on different technologies, not exactly the same, but there are 3 other cameras, but all of them are on relatively small telescopes, telescopes that are only 15 to 10 meters in diameter. So what's really special about Toltec is the combination of Toltec and the large millimeter telescope, which is 50 meters in diameter. So this telescope, it's hard to see in the picture behind me, but you know, there's a big crane there, there are buildings. I mean, that telescope is enormous. And it's the combination of the huge area for collecting the light and then the very powerful camera of Toltec behind it. That's what opens up the new observing of the universe. So other cameras on small telescopes take very coarse, low resolution images of the sky, where, you know, hundreds of galaxies would be merged together in the same blob. With Toltec, we have enough resolution to go and pick out individual galaxies or individual areas of star formation. So you can do much more detailed studies. And that's why people want it.
Paulina?
Yes, so this is really interesting. You're like a time traveler every time you're in,
Right.
in the telescope. So astronomy has changed and shaped humans' understanding of life since the beginning of time. Many ancient cultures, such as Mayans, used to observe the behavior of the sun, the moon, and the stars, and adapt their habits around the behavior of this. Everything from religion to agriculture was influenced in some way by astronomy. So in these modern times, how would you think a better understanding of the universe using all this cutting edge technology will shape and change the way we understand life?
Yeah, that's a deep question. I think of our work contributing in that way in two very different ways. So first, you could justify almost all the astronomy work that's done around the world based on the technology development that happens just to make the astronomy possible, to be able to do the observations. And so just to give you an example for Toltec, there is already spin-off technologies from our detector development and the detectors we use to make it possible to get rid of X-ray machines at airports and instead just have cameras like Toltec that watch people walk by, where you can see any concealed weapons that they will have, but completely passively, only from the radiation that you and I emit naturally as we're just sitting here. So there's lots of spin-off technologies from what we do. To go the other way, why do that for astronomy? We've had a lot of writing in the news lately about aliens and who we might share our galaxy with. And I think in a very deep existential way, we have a responsibility to understand the universe we live in, the galaxy that finds itself in the universe. How did this form? How did our planet form around our sun? These are all areas that we can touch with the kind of astronomy we do with the large millimeter telescope. And then ultimately, who do we share this galaxy with? And what questions come, you know, along with what technologies they might have, or or what's going to happen when they visit, and things like that. So I don't know if that answers your question, but
Yes, it does.
these are the kinds of things I think about when we're studying the Milky Way.
Yeah, this brings a lot of questions to my mind about deep questions like this about the understanding of life and how we would understand it if at the end we found that there's some other thing living out there.
Yeah.
So
yeah,
right. let's hope and see how things go.
And I guess I know that one of the challenges is getting Toltec to Mexico, and pandemic didn't help much, I suppose. How is the process looking? Do you think it will soon be able to reach Mexico?
Yeah, I'm very.
And what final words would you want to share with us?
Well, Right. So I'm very happy to say that the first shipment of Toltec parts has already gone,
Oh, okay.
and is at the airport in Mexico City right now. So the first steps have been made. I was just on a call prior to this one with our colleagues in Mexico who reported that they are now getting the second doses of vaccine for all people over 50. So I'm very happy to hear that. And it sounds like the COVID situation will one day be under control thanks to the vaccination program. So I think that the news is very good. We hope to be reopening the telescope shortly because it's been closed because of the COVID pandemic. And so this timeline we're looking at is that the telescope will open shortly when it's safe for everyone to travel and regularly congregate at the telescope. We hope we are literally packing Toltec right now. My students in the lab are taking the camera apart and putting it in boxes. We hope to ship around the end of this month. And if all goes well, it will be safe enough for our team to meet up with our colleagues in Mexico and start installing the camera in August, or right at the end of the summer. So we're very optimistic that this year, 2021, we'll see what astronomers call the first light, the first amount of light coming through the telescope and getting to the camera. And we hope to have early results to share with the world soon after that. So we're very positive. You know, the pandemic has been so hard on so many people, and we didn't talk about the ways different cultures approach it. But I'm really hopeful that the progress we've seen with the vaccine here in the United States is replicated in Mexico, and that we see the disease come under control there.
Yeah, well, it seems most of the countries now in what we call green zone.
Yeah.
So hopefully it will be getting better and better, and hopefully you'll be able to be there in August. It sounds fantastic.
Yeah, well, we can't
hopefully
wait.
we can go visit you also to UMass Amherst once you reopen for general public.
We'd love to have you here, and we'd love to invite you to the telescope sometime when you're in Mexico. So please come visit us.
Of course. Well, thank you so much, Professor Wilson. Thank you all for being with us, learning about this fantastic international collaboration that will help us understand more about our galaxy, our universe, and who we are as part of it. Thank you so much.